After structuring the dataset according to the purpose of AI, we now turn our attention to how to train it. We've already covered learning methods, including supervised, unsupervised, and reinforcement learning. For vision deep learning, our focus will be on supervised learning. Regardless of the learning method, it's crucial to divide the original dataset into distinct parts. This division is a standard practice in machine learning to ensure effective model evaluation. This separation helps in mitigating overfitting and allows for the independent assessment of the model's generalization capabilities to new data. The dataset is typically split into three parts in machine learning: training set, validation set, and the test set. Let's define what each of these datasets are and what they are meant for. Training dataset, this is used for learning. It's the data we input into the model to train it. The training dataset is fundamental in teaching the model to recognize patterns or learn behaviors. It consists of numerous examples through which the model iteratively adjusts its weights and biases to minimize errors in its predictions. So the difference between validation and test sets may be a little confusing, as the definitions of validation and test are similar. So validation test set. This is utilized to evaluate the model while it is being trained on the training set, allowing for the tuning of model parameters and the prevention of overfitting. Next is test dataset, employed for the final evaluation after the model has met its performance goals. This dataset helps verify that the model performs well on entirely unseen data. This process of final evaluation ensures that the model's learned behaviors generalize well beyond the scenarios and examples encountered during training, thus providing a realistic measure of its performance in practical applications. During training, as you'll see in the practical sessions, we input an initial dataset and iterate over the training process several times to enhance the model's accuracy, ideally nearing 100%. However, this accuracy pertains only to the training set, the data the model was specifically trained on. It's crucial to test the model on new, unseen data to ensure it generalizes well beyond its training data. An analogy here is like a student studying from a worksheet to refine their understanding of specific concepts. Just as a student learns from specific materials, the model learns from its training data. Concurrently, the model's performance is tested on the validation set. While the training set often shows higher performance because it's the data the model learns from directly, the validation set acts as a reality check to assess if the model is learning effectively and generalizing its knowledge rather than just memorizing. Ultimately, the validation set helps determine when the model is ready to be evaluated on the test set, ensuring it has been adequately trained and is ready for final performance verification. However, it's important to watch for cases where the model performs well on the training data but poorly on the validation set, which may indicate overfitting and a lack of generalization to new data. To better distinguish between performances, we'll change the colors used for training and validation data. Normally, loss or error will be placed on the y-axis, but for simplicity's sake, we'll use accuracy here. Typically, the training dataset shows improvement over several iterations due to the model learning directly from this data. As a result, on the training data, the model may score close to 100%. To ensure that the model is learning effectively and not just memorizing the data, we observe how the accuracy trends over iterations. This trend analysis helps validate that improvements are due to genuine learning processes, essential for the model's ability to generalize beyond the training data. If the model performs well on the validation set, though usually slightly lower than on the training set, we can progress to evaluating it using the test set. This test set is crucial for validating the model's performance in real-world scenarios. The slight performance dip from training to validation helps identify any potential overfitting issues early, ensuring that the model's efficacy is not solely tailored to the training set, but is adaptable and applicable under varied conditions. For instance, a model might achieve a perfect training result with 100% accuracy, perform at 95% on the validation set, and reach 93% on the test set. This trend illustrates how performance can vary across different dataset splits, highlighting potential overfitting to the training data while still maintaining a robust generalization to new, unseen data. To provide an analogy, imagine the model's training process is like a student preparing for a test. A student may use a workbook to study. The training set is like the workbook problems they repeatedly practice and learn from, which helps them perform well, but doesn't guarantee the same results in a real test scenario. The test set, then, is similar to the final examination where the student's comprehensive knowledge is truly tested, independent of the practice materials. This final evaluation helps confirm the model's ability to generalize beyond its training. So, in this case, what would the validation set be? In this scenario, the validation set is similar to the practice test a student takes before taking the final exam. These practice tests are used to assess the student's current level of understanding and preparedness for the actual test. Based on how well you perform on the practice test, you can gauge your potential performance on the final test. However, since the scores from the practice test are not final, serving primarily to assess a student's current standing, they are similar to a validation set, which provides ongoing evaluations throughout the preparation period before the actual test. I'll provide another example. Consider a musician preparing for a live concert. Before the actual performance, they might have several dress rehearsals. These rehearsals allow the musician to practice a set list in an environment that closely mimics the live show. The feedback received during these rehearsals regarding timing, coordination with other musicians, and overall execution helps refine the performance before the main event. Like the validation set in machine learning, these rehearsals serve as crucial checkpoints to assess readiness and make necessary adjustments. They are not the final performance, but are essential to ensure the musician is well prepared and confident, mirroring how validation sets help tune machine learning models before they are tested in real-world conditions. Overall, this analogy highlights the importance of systematically partitioning data into training, validation, and test sets to effectively train, fine-tune, and ultimately validate machine learning models, ensuring that they are robust and perform well on the new data that they are received. Now that we've covered the division of the initial dataset for training and evaluation, let's explore common methods used to assess model performances based on this segmentation. First is holdout validation, where after setting aside the test set, a portion of the remaining data is designated as the validation set. Consider an example from medical vision deep learning. Suppose we start with 1,000 CT scan images. We might reserve 10% or 100 images as the test set. Of the remaining 900 images, 200 could be used for validation and the rest, 700, for training. This method involves splitting the initial dataset into different proportions according to specific needs. You might wonder what the optimal way to divide the dataset into training, validation, and test set is. While there is no definite answer, the general practice is to allocate a substantial portion to the training set to expose the model to as many examples as possible. However, we must also reserve enough data for validation. This distribution strategy aims to balance the breadth of learning with the necessity for robust model validation. Ensuring enough data in the training set helps the model learn effectively, encompassing a wide variety of scenarios it may encounter. Conversely, the validation set is crucial for tuning the model's parameters and preventing overfitting, which is when a model performs well on the training data but poorly on unseen data. Typically, the split might look something like 80% training, 10% validation, and 10% training, or 70% training, 20% validation, and 10% for testing. In all these divisions, we see that we prioritize the training set while ensuring sufficient data for validation and testing.